Okay guys, let's start revising for exam. I am starting with electric circuits just because it is the most recent module that we looked at, and I want to give it a little bit of time to percolate. So it is new work, so our brains need a little bit of time to get used to the information. So I'm doing it now so that it has all the time up to the exam to brew, if you will. I want to go on a little bit of a tangent just before you begin so that you understand the way that I'm going to answer these exam questions. So remember, there was a time that I told you that learning is state specific, meaning the way in which you learn will be the way that your brain is going to want to remember the information. Okay, so keeping that in mind, there are a couple of ways that you can do this revision with me. The one option is just to listen. So put your earphones on, go for a walk and just listen to what I'm doing. And your brain will use my sound waves over the headphone and it'll store that information somewhere in your brain. And it might, under the correct circumstances, if you are as relaxed as going on a walk, it might be able to retrieve that information. Another way is to not only listen but also to watch. So then you're using a second sense, which gives your brain an opportunity to store the information in some other part of your brain as well. Now, the problem with only listening and watching is that those are very passive activities. You don't really have to move a lot to listen and to watch. But think about writing an exam. Would you say writing an exam is a passive activity or is it an active activity? Now, I hope you agree with me that writing an exam is actually very active. You are busy, you are tired when you are done. So in that regard, to help your brain to learn in a state-specific way, meaning in a way that you are going to need to remember it, we need some movement. Now, one of the ways that we did movement during the school camp was that we painted and we also did some sewing. Okay, so that was for chemistry. We haven't really done anything active for circuits. So for this one, I would also highly encourage you to pick up your pen and do the sums with me. Again, all of this is designed to help your brain remember it in the most efficient and easiest way. Okay, we want to work smarter, not harder. Now, there's one more reason why I want you to write this down. You might know this picture. Did you know that our brains cannot see themselves? So our brains are constantly busy with things that it's thinking about and plans that it's making, but it doesn't have a way to double check itself. So your brain might believe and think that it's a cat, but it might actually be a lion. Okay, so we write it down so that we can see our mistakes. So we give our brain the opportunity to see itself and make sure, hey, is this what you thought you're doing? Is that really what you're wanting to do? Okay, and now, I mean, we can talk the whole day about this little picture, but it just comes down that you are more than you think you are. Okay, so with that in mind, let's start revision for electric circuits. Now, the process I'm going to show you today, it might frustrate you a little bit because it's new, but there is method in the madness and it takes everything that I was just talking about into consideration. So the first thing that we are going to do, we are going to read through the paper just like we would in the exam. So in the exam, you have about 10 minutes reading time, and during that 10 minutes reading time, you are allowed for the science paper to use your highlighter. Okay, and we are going to read through it and just highlight the important things, the things that we think are important, that we want to see next. Okay, so these are our instructions. So this assessment paper consists of 16 pages and then questions. Please make sure that you have all the pages. Find the formula sheet and constant values below these instructions. So these are our formulas. We'll have a look at them now. You do not have to do the questions in order. For ease of marking, number your questions clearly. Show all the formula, calculations, and diagrams that you use to answer your question, and round all answers to 2 decimals. Now, just a note on the rounding, that is for your final answer. If you have multiple steps, especially like when we do circuits, you can round them, but don't use the rounded numbers in your calculator because your answer will most probably be wrong. Especially if we round to 2 decimals, then the error factor becomes quite big. Okay, so if we look at our formula sheet, V is your potential difference, that is your volts. I is your current in ampere. R is your resistance in ohm. W is your energy, that's in joules. And T is time in seconds. Now this one, the explanation of the symbols won't be included in the exam. That you need to know. But the formulas, these 3 formulas you will have. And what I'm quickly going to do I am going to write myself little notes about these formulas. So V is voltage, I is current, and R is resistance. So this first line that I just told you won't be included in your formula sheet. I'm writing it down now so that I can come and reference them. So that I don't have to remember V is voltage. I can just see V is voltage. Okay, I is current. I'm not going to write that again. Q is your charge. T is your time. And then the other ones I have as well. Okay, so let's read. Question 1 is true or false. Indicate whether the following statements are true or false. Now, I know we've done this in class, but pretend that you haven't done it, okay? So electric current is defined as the quantity of charge that passes a given point in a conductor each minute. So the important words here are electric current is defined as the quantity of charge, let's talk about charge, that passes a given point each minute. Okay, I'm not worrying about the answer right now, I'm just looking for important words. Two cells are connected such that the positive terminal of the first joins the positive terminal of the second. Then we say the batteries are connected in series. A joule is equivalent. Now equivalent is the same as equals. Volt per coulomb. So per is an important word. And then 1 ampere again equals 1 coulomb per second. And then the last one, Ohm's law states that voltage is directly proportional to current and indirectly proportional to the resistance. Now, if you know your theory, especially if you know what's going on in your formulas, you might already know what the answers are, but I want to encourage you not to jump to conclusions. Okay, we're going to do it nice and slowly. Because sometimes, as you saw in class, you think you're right and then you're actually wrong. The next one is give one word for. So a voltmeter is usually connected in series or parallel. I need to figure that one out. A measure of how much charge is passing a certain point in a circuit in a given amount of time. The apparatus, the phi, used to measure the potential difference across a resistor. The amount of energy that the battery gives to every charge that passes through it. And then the law. We only have one law in circuits that says current is directly proportional to voltage provided that the total resistance remains constant. Okay, next one. This one is multiple choice questions. Choose the correct answer, only write the letter of the answer that you select. Now I'm going to use my pencil as well because the first thing that I'm going to do here is I'm going to redraw it in the way that we've been practicing. Remember, learning is state specific, né? So if you've learned and practiced electric circuits in this way, then please do it the same way in the exam. Okay, so that is 2 ohm and 4 ohm. And then they're asking us something about the current. Now, we remember the current is the same as our ferries, right? So we know the current splits up. So we know that the total current equals the current in leg 1 and the current in leg 2. Now, you will see that I have ignored the 1, 2, and 3 because I'm not worried about the question. I'm just worried about getting my facts straight about what they're giving me. 3.2, again, we have a little parallel circuit over there. There's the battery, the 1. So these are circles because they are bulbs, but you can make them resistors as well. So here they want to know what's happening with the voltmeters. And we know the total energy of the battery, because we only have one obstacle, will be the same as in leg 1 and it'll be the same as in leg 2. And I've now decided this is leg 1 and this is leg 2. I haven't actually looked at the question. Okay, the unit in which the rate of flow of charge is measured. Now, rate of, I told you, was divided by T, right? And it's charge. So I'm looking for Q over T. Then the energy transferred per electric charge. So transferred per electric charge. That's what they're asking in 3.4. And then they're asking for ohm, and now they have a couple of options here. It's 1 volt per coulomb, volt per joule. So I need to go figure out how can I write R. So which symbols can I use to write R? And we're going to use our formulas, but we'll do that when we actually answer the question. Then the unit of measurement for electric current. They want to know something about electric current, so I need to figure out, and not remember, I'm just going to reference because I already wrote it down. I need to figure out, or remember, or reference, how to write I. 3.7, which of the following statements about resistance of a wire is correct? Okay, so this is the factors. Now, I am not going to try to figure out any one of those. I am just going to remember, what was it, lumped. So we have length. There we remember we have a direct proportionality, and temperature was also a direct proportionality. We didn't really have notes for material because it depends. And then with our area, just going to write it a little bit smaller, 1 over A is directly proportional to R, or R is indirectly proportional to A. That's all that I'm going to do now, and I'll come and test these statements with my little scribbles over there. Okay, 3.8, we have this parallel thing again. Seems to be a thing. So there's my little battery. And I wonder if you're doing this with me, if you can feel that there is a sense of comfort when you draw this over and over again, because it's something that you know. Now they're asking us something about the current again. And we know current was the team of fairies, right? So it's going to split up. And I'm going to decide this is number 1 and this is number 2. So I know my total current will split up into 1 and 2. Okay, so again, I haven't really looked at the answers yet. And I'm doing that on purpose because the answers are going to freak me out. Then we have 10 coulomb of charge passes a point in a circuit in 2 minutes. And then they're asking for the current. So I'm just going to make a very quick information list. Charge is Q. So I have a value for Q. That's 10 coulomb. And then they give me time in minutes. That's 2 minutes. So it is 120 seconds. And they're asking for I. I'm not going to determine it now because I'm still busy with my reading time, and I'm not allowed to write anything. The resistors connected in series are called dividers of what? Okay, so we touched on it very quickly in class, and if we go back to this one, we can see that when we have parallel circuits, the current is divided. So the current divides, and if I have series, it means the other one, so voltage is divided. And I'm not looking at the answer. I'm not trying to put the answer down now because that's really not what I'm doing now. I'm just reading and highlighting and information dumping. So consider the following statements regarding voltmeters. And then they've got a couple of here. And this one, I would actually skip completely if I were writing this exam because it's a lot of information and I don't want to get hung up on this. But let's read. So we're talking about voltmeters. So the reading of voltmeters connected across resistors is inversely proportional to the resistance. Okay, so there we've got the voltage and the resistance, and they say it's inversely proportional. Now, Ohm's law helps us to get voltage and resistance next to each other so that we can observe them. When a switch in a circuit is closed, a voltmeter connected across a battery reads the EMF of the battery. I don't know if I told you this in class, but this is actually true. So the switch is closed and then it's the EMF. Voltmeters connected across equal resistors which are in parallel will give the same reading. Now we know this is true as well because we've had a couple of examples. I know we've been doing the current, but if the current divides, then the voltage needs to be the same, and that's part of our theory. So resistors in parallel will have the same reading, and voltmeters are always connected in parallel. Okay, and we'll come test all of these when we get there. Okay, now on to question 4. So again, what I'm doing is I'm highlighting the important information. All right, and what I will do here is I am going to redraw them very quickly. So this is a parallel circuit. We come out of the battery and then there's a junction. So I need to choose. And because I need to choose, it looks like this. This is the way we've been drawing it, right? Okay, state specific. Exactly the same way that you learned it. And then circuit B is just a series one. So there's the one. There's the other one. And I'm going to stop here. I'll come and add the numbers later when I come back. So the first one is just define the term EMF. Then they want the total resistance of current A. And then this is all about circuit B. It's this one or that one. And then they want to know the reading on A2. That'll be that one there. And then calculate the reading on V1. That'll be that one over there. If we just go back to the yellow one, they're asking the total resistance. So it will be the resistance over here at the battery. Okay, and then the last question is if a third resistor is placed in parallel with the existing resistors in circuit A, would the total current in the circuit increase, decrease, or remain the same? Explain the answer. So this is a little bit of an intense one, and I'm going to definitely leave it until last in the paper. because I need to wake up my brain first. All right, question 5. In the circuit diagram below, the reading on voltmeter V1 is 12 volts, and the reading on ammeter A1 is 2 ampere. Now, before I read the questions, I want to redraw my circuit. So we come out of the battery, we have the 4 ohm one. Then past the 4 ohm one, we have a junction, so we have a parallel piece. And this one is 6 ohm, and this one is 3 ohm. All right. And then from the words of the question, I know I have the value of A1 and V1. And the rest I will come and put in when I do my information list. So they're asking for the total resistance of the current. Then they're asking for the value of V2, A2, and then the amount of charge that flows through ammeter A1 in 120 seconds. So here they give us time is 120 seconds, and they're asking for the amount of charge. So they're asking for Q. Okay, so that's just like a little information list for now. And then 5.5, how will the reading on ammeter A1 be affected if the 6 ohm resistor is removed from the circuit? So this question 5.5 is very much the same as question 4.5. So if you can do 4.5, then 5.5 will be easy. And then 5.6 asks for explain your answer without using any calculations. So this one is an easy one. It's just a circuit in series. We have 2 identical light bulbs. So because the light bulbs are identical, we know the resistances are the same. And then we have a measuring device Z. Now because Z is inside my current, it's in series. We know it's an ammeter. And there's also a battery. And then they're asking which physical quantity will device Z measure? And I would just take my pencil and just write there, that'll be an ammeter. And that measures current. Give a reason why the brightness of the bulbs will be the same when the switch is closed. Okay, so brightness you saw in the video. For this year, you can just say brightness is directly proportional to current. So whatever happens to the current will affect the brightness. And then a third identical bulb is now connected in series. And what will happen to the brightness. So they're basically asking you what's going to happen to the current. And we'll figure that out now. Question 7. In the circuit below, potential difference V1 across the battery and potential difference V2 across the 4 ohm resistor are unknown. Okay. When switch S is closed briefly, the potential difference across the parallel combination is 4 volts. So this is the first actual value that they give us, and that's that one there. Then they ask define the term potential difference. Now potential difference is one of our definitions that comes straight from here. There's the definition. I just need to put it in words. Then they're asking for the effective resistance of the 2 ohm and the 6 ohm resistors. So 2 ohm and 6 ohm, that's the parallel piece. So when they're asking for the parallel resistance, they're also asking for the effective resistance. It's another word that they can use. And then we want V1 and V2. Now I'm sure I've drawn this one before, and it brings me great comfort to just draw it again. And you can decide how much time you want to spend now. Do you want to do the information list now, or do you want to do it when we do the sum from start to finish? And that's sort of up to you. If I'm very stressed, for me, I would actually take the time now and just information dump everything now so that I don't have to stress about it later. But also, if I'm very stressed that I am not going to get done with the exam in time, maybe because I don't feel prepared enough, I might just do this and then come back with the information list later. So it really, really depends on how you're feeling on the day. Okay, we're almost done with the reading. In the circuit diagram below, 3 identical bulbs are connected as shown. The ammeter connecting wire and battery have negligible resistance. Study the diagram and then answer the questions below. Okay, so again, the same one. So P, M, and N are my bulbs, but I'm going to draw my blocks because they make me feel nice and fuzzy and safe. When I do circles, it's different from what we've been doing, and that freaks me out a little bit. Okay, so they say switch S1 and S2 are open. So if S1 and S2 are open, then do you agree no current is going to flow? The fairies won't be able to get back to the battery if your 2 switches are open. So they're asking if any lights, if any bulbs will light up. And the answer will be no, right? Because the bulbs will only glow when fairies go through them, when current passes through them. And then now they say S1 is closed and S2 is open. Compare the brightness. So if this one is S1 and this one is S2 and they tell me S2 is open, then this whole leg of the parallel piece will just be ignored because the electrons can't go through there. And again, they're asking about the brightness. So just like one of the previous questions, here they're asking about the current. So the question is about the brightness of the bulbs, but the answer, you have to go through the current. Okay, then choose the correct words below. Parallel circuits can be regarded as current or potential dividers. Now, I don't know if you've noticed, but we had that same question in the multiple choice questions. And I already made a note about it. I haven't decided on the answer just quite yet, because I'm giving my brain a little bit of a chance just to process the information. But this question isn't freaking me out because I know I've planted the seed for the answer. Adding bulbs in parallel causes the resistance of the circuit to increase, decrease, or remain the same. Now, we've had a similar question earlier, so I don't know the answer actually quite yet. I haven't figured it out, but I know I will. And then potential difference across the battery. There's something wrong with this question. Potential difference across the battery to increase, decrease, or remain the same. Okay, so this is a weird question. I have no idea what's going on there. So it might be that I'm not understanding the question, or it might be that there's a mistake on the question on the paper. But whichever way, I'm not phased about it right now. I'm just reading. Okay, question 9. Then we could do question 10, and then we're done with the reading time. The current diagram below consists of a battery, a switch, ammeter, and a glowing light bulb connected in series. A voltmeter V1 is connected across the light bulb. So just for pattern completion, and because I know it helps me to feel nice and fuzzy and comfortable, I'm redrawing my circuit without the ammeter. I'm only concerned about the resistors or the light bulbs. Then they're asked to find the potential difference. That we can do because it's in our formulas. Define electric current. That I can also do because it's in my formula. And now they give us information. They tell us the ammeter A is 0.6 ampere and we've got some energy going through in 3 minutes, and they're asking for the V value. So I'm going to make a quick information list here. So my I value is 0.6. My W value, that's your energy, is 486 joules. And then my time, they give it in 3 minutes, so I just need to multiply it by 60 to get your seconds. And then maybe I can just write that one V. Then I don't have to read the question again. All right, and last question, question 10. Consider the circuit below. The bulbs are identical, so because the bulbs are identical, I know the resistances are the same. The resistance of the battery, ammeter, and connecting wire can be ignored. That will always be the case in school circuits. Now they ask, wait, first, let's just draw it. Now, I notice now that this is the very first time that I have 3 resistors in parallel. But I'm not too phased about it because I know that the theory we've been working with is exactly the same. It's not going to change. I have to adjust it because I have 3 instead of 2 in parallel, but the idea will be exactly the same. So calculate the voltage of all 3 cells if they transfer 90 joules of energy to 20 coulomb of charge. So we have some information there. My W value is 90 and Q is 20, and they're asking for voltage V. And there's a little bell that's ringing that I have a formula that I might use there. Then they ask, what would the potential difference of each cell be? Okay, so here we just need to differentiate between the battery, which is this whole thing, and a cell. So we've got 3 cells there. You can just make a note there. There's one short, one long, that's one cell, and then we have short, long, that's your second cell, and then short, long again. So we have 3 cells. And then determine the current through each individual light bulb. And then if one of the bulbs burn out, how would the brightness of the other 2 bulbs be affected, right? Shine brighter or shine dimmer? And we know now with brightness, they're actually asking for I. So they want to know what's going to happen to the current, the number of fairies moving through the legs if one of the bulbs burn out. And then we are done. So we are done with our reading time. Now we can actually start tackling the questions. And I'm not going to start at question 1. I'm not going to start at question 2. Those are difficult ones. I'm not going to start with question 3. It's a difficult one. Not difficult really. It's just your brain has to work really, really hard to find the answers. So I am going to start at question 4. And because I have now 2 circuits, and we haven't really done 2 circuits altogether, and I feel a little bit freaked out by the fact that there are 2 circuits and not only just one, I'm going to start with question 5, because that one is the one that makes me feel the safest. Okay, so let's have a little transition. You would have noticed that I didn't once ask myself whether I can do a question or not. I was only concerned about the information. I was just highlighting the information that I'm going to need now when I'm going to try and do the question. The other thing that you would also have noticed if you did it with me, that we took a little bit more than 10 minutes for our reading time. Now there's 2 factors. I was speaking and I was making notes all together. When you're going to do this on your own, you won't be speaking, you will only be making notes. But it is totally fine if you take more than 10 minutes for the reading time, because this, even though it seems like we were doing nothing, is actually laying a foundation so that we can do all these sums much faster. Okay. So let's just read this question again. All questions you always read 3 times. Once to figure out what's going on, that I've just done. Second time is to figure out exactly what needs to go where in terms of information. And then the third time we read it again to make sure that we answered it in the correct way. So in the circuit diagram below, the reading on voltmeter V1 is 12 volts and the reading on ammeter A1 is 2 ampere. And then they have a bunch of questions. Now, I am going to assume that you are not very fluent in circuits yet. So you're still trying to find your feet in terms of what do you know, what don't you know. So I'm going to do it the long way with all the information lists and all the theory. Okay, so this was the summary I also made on the board in class. And what I decided is that I'm going to change the orientation just a little bit so that it looks like this. And then I have my VIR information lists. And then the last thing I need to do is just put my highlighters in, because I don't want to think and think again. I don't want to remember and remember again. I want to remember now and I want to get it all done with. Okay, and that is my preparation for the sum. Now I have one of 2 ways of doing this. The one way is just to fall in and determine all the variables and then go and look at the questions, which is actually my preferred way of doing because I like to complete things. The other way is to actually look at the questions and then answer them in order. So I want to show you that you're actually not going to lose time by doing all of them. Okay, so I'm going to start the timer and we're going to determine all the unknowns. Okay, so the first thing that I'm going to do, there's actually a couple of things that you can do. Let's start with this one. I can see there I have a 2 out of 3 count. So V equals I times R, and I'm working with my T values. V is 12, I is 2, I need RT. So to get RT alone, I'm going to divide the 2 to the other side. So 12 divided by 2 is 6 ohms. Now, if this bothers you, you can swap it around to say RT equals 6, but I'm not too worried about that. Okay, now, just because it's something that I've just seen, the sequence will be different every time. There, if I use those values, I can use this formula over there to determine RP. Okay, so let's do that. So RT equals R1 plus RP. RT I just calculated as 6. R1 is given as 4 and RP is unknown. To get RP alone, I need to move the 4 to the other side, so it's going to become 6 minus 4. So that's 2 ohm. Okay, so I can write the 2 over there. Now I can also come and this IT value, I can come and write there, and I can write it there. So I've used this formula now, and I've used this formula. Okay, and then Ohm's law, I'm just going to use continuously. Let's see what else. Let's do this one. So VIR, I'm working with my P values. Then IP is 2, and RP is also 2. So here I get, let's put it there, 4 volts. So I can put it over there. Okay, let's do purple for this one. So same story, VIR. Now I'm working with my 1 values. V1, I want to determine I1 is 2, R1 is 4. So here I get a value of 8 volts. And there I can put it over there. All right. Now I can use this formula just to double check myself and make sure that I'm actually on the right track. So that formula tells me Vt equals V1 plus Vp. So that's the energy, right? The energy that the electron carries with it. So it's going to collect some energy. In this instance, it's 12 volts. It's going to use 8 volts over here. And when it passes through the parallel piece of my circuit, it's going to use another 4. So we just need to make sure that these numbers actually add up. Let's pretend I didn't have Vt. So I'm going to say V1 is 8 and Vp is 4. And then I do get a value of 12 volts. So I just double check myself to make sure that I'm on the right track. Okay, I'm just moving them around a little bit because I don't have a lot of space. I would just carry on to the next page if I were you. Okay, so we've calculated all the values in the main circuit. So let's try this little one and just make sure that everything works out. So because I use my blue highlighter, I am reminded that that 4 I can write over there and I can write it over there. So again, V equals IR. And now I'm worried about the 2B values. So I'm using those as subscripts. V to B is 4. I just wrote it down there. And I know it's equal to VP because there's a little formula over there. So I just used that formula. And it's on my paper that I'm going to hand in for marks. So if this little formula, where's my cursor? If this little formula is needed for a mark, then it's on my paper. Okay. I want to determine, and then R was 6. So if I want I alone, I need to divide by 6. So 4 divided by 6 is 0.66. And we need to round to 2 decimals, so 0.67 amperes. Okay. And I can write that there, 0.67. Now, if I keep this in mind, then I know whatever I to B will be, we need to get to a value of 2. So we will have another opportunity to just double check ourselves. Okay, so again, V equals IR. Now I'm worried about, what did I do there? That's supposed to be an A. Sorry, guys. Okay, so I made a mistake, but because everything is on the paper, it's easy for me to fix my mistake. I don't have to redo everything. Everything's there. It's probably going to happen again. I am renowned for writing mistakes. So V to B is 4, that one is I, and that one is 3, and then if I want I alone, I need to do 4 divided by 3, and that is 1.33 amperes again. And 0.67 plus 1.33 indeed does give me 2 ampere, so I know I am right. Okay, so the time on my watch is now 12:40, which means that we use about 7 minutes to do all these calculations. All right, let's go back to the questions. And please have your little booklet with you because I'm going to be paging forward and back and it's going to get confusing. And I'm going to tidy this up now because I know it looks really, really rough. The first question they ask is determine the total resistance of the circuit. Now, the total resistance of the circuit, I should have highlighted that maybe before we started, but that's that, okay? And that is exactly what I did here in pink. So what I'm going to do now, I'm going to draw a little block. And we're busy with question 5.1, so I'm going to write 5.1. The next question is the reading on V2. Now, V2 is the voltmeter reading over the 4 ohm resistor. So you would have noticed that I used just my own numbering system. And that's fine because I was taking the control onto myself. Now I just need to change it a little bit so that it actually fits the sum. So I want the voltmeter reading over the 4 ohm resistor, and that would be that one, okay, which ended up as V1 in anyway. Now I did that in purple, and that's what I did there. So this is 5.2. And to do 5.2, I had to use the fact that IT equals I1 equals IP, and it's on my paper. So if this is actually needed for a mark, it's on my paper. It's not necessarily next to my answer, but it is still on the paper, so I can get my marks. Then A2 is the current of the 6 ohm resistor. So the current of the 6 ohm resistor, so that's that value over there. And that's what we did in light blue. So that would be 5.3. And then, okay, then they ask for a little sum, and then there's something else, and then there's something else. So for these 3 questions where I had to do calculations, that is 10 marks. And 10 marks equates to 12 minutes. Okay, so I had 12 minutes to do those 3 sums. And I only used 7, even though I did a little bit more than what I was supposed to do. Okay, so what I want to show you, prove to you with this example, is this method, even though it feels like a lot of work, it's actually saving you time in the long run. Okay, now I really hope you did this with me on your own piece of paper. And I also hope that if you didn't use color, at least that you drew little blocks around the answers. So, depending on how fast you write, I wouldn't recommend this way, but I have had students that do it this way and they were fine. They did it, and you can see you have enough time. I mean, we have 5 minutes to spare. And drawing out the circuit wouldn't have taken more than 2 minutes. So we still have time. So I've had students that did this as rough work in pencil, and then they just erase everything that they didn't need. I don't erase that because there are marks there. But you could erase that and that and that because that's unnecessary. And this was just me checking myself, so that's also unnecessary. So you can clean it up a little bit if you do everything in pencil first and then copy it in pen. But remember, I can only give you marks if it's in pen, so it needs to be in pen. While you're practicing, I actually recommend do it in pencil so that you can erase the stuff. All right, so in terms of the sums, we are done now. Now 5.4, they ask for the amount of charge that flows through an ammeter A1 in 120 seconds. Now I already have half my information list, and I know from my formula sheet that to determine the charge, I need the time and my current. So they are basically asking, first find the current in A1. Now A1, they actually gave us, is 2 amperes. So let's do it in pen. So they want to know charge. They gave us time, it's 120 seconds. Time needs to be in seconds. And then my current is 2 amperes. And to determine current, we say it's Q divided by T, because current is the rate of flow of charge. Q, I don't know. T is 120, and then I is 2. To get Q alone, I need to multiply my 120 to the left. So it becomes 2 times 120 equals Q. So Q is 240, and the unit is coulomb. And there you are done. Now what I want you to see in this black writing over there is I didn't really do anything. I just copied, because I did this in my 10 minutes reading time. So I copied the information list into pen. I wrote the formula just into pen because I already have it. And then I did substitution, and then I solved it, and then I have my answer. So you have all your marks. You have a mark for your formula, you have a mark for your substitution, and then you also have a mark for your answer, provided that you have your unit there. Okay, so we had a total of almost 4 minutes to do this sum. And with the preparation, it would have taken you less than a minute. Now let's look at the next one. They say, how will the reading on ammeter A1 be affected if the 6 ohm resistor is removed from the circuit? Okay, so let's just quickly draw the circuit before and after the change. We actually have done it before because we just use it for the sums, but just humor me for a second. So if I remove the 6 ohm resistor, this one over there, it's just going to fall away, right? So then we end up with a series circuit. Now A1 is our total current. So they are asking us what is going to happen to the total current. Now we know from Ohm's law, V equals I times R. All right, now our V value, our VT value, that is only dependent on the battery. So this value is going to remain constant. Okay, they want to know what's going to happen to the I value. And to figure out what's going to happen to the I value, I need to figure out what's going to happen to the R value. So what's happening to the total resistance of the circuit? Now, luckily, we actually have a calculation. We know the total resistance of the original circuit was 6 ohm. So here we had a total resistance of 6 ohm. Now in this next circuit, I have a 4 ohm resistor and I have a 3 ohm resistor, okay, because we took the 6 ohm one out. So do you agree that for my next circuit after the change, my total resistance will be more? Okay, now I know it's a little bit confusing because we took one out, but now the resistance is more, and it's just because it was in parallel. And if you really want to understand it, it comes down to this little formula over there. So mathematically, that's why, if you want to understand it. Okay, so let's see if we can figure this out. Okay, so we just proved to ourselves with a little calculation that my R value increased. Okay, and because my R value increased, my I value needs to decrease so that my voltage can remain the same. Okay, so I'm going to say it again. So we start with Ohm's law. It's always going to be Ohm's law. And we work with the totals. Okay, so if my total voltage needs to remain constant because I haven't changed my battery, your total voltage is only dependent on your battery. My battery hasn't changed, so my voltage can't change. By doing a little calculation, and you can remember it, it's now part of your knowledge, that if we go from a parallel circuit to a purely series circuit, the resistance will increase. So that's what that said. So the resistance increased. And because there is an indirect proportionality between I and R, I needs to decrease. So the answer here is decrease. Okay, now for this one, 5.6 is explain your answer without using any calculations. And it means that they want this. They want your reasoning there. And the way we write it looks like this. Okay, so first we're going to start and state Ohm's law. So Ohm's law says that current is inversely proportionate to resistance, provided that the voltage remains the same. So if you have 3 variables, one will always need to remain constant, else this whole proportionality thing won't work. Okay, so I state Ohm's law. Current is inversely proportionate to resistance, provided that the voltage remains constant. Okay, now I'm telling them I understand that when we go from a parallel circuit to a series circuit, the resistance will increase. All right, so I'm stating something that I know. I'm stating something that they told me is going to happen, and now I'm making these two fit in my last sentence. Therefore, if the resistance increases, then the current will decrease, provided that the voltage remains the same. Okay, so can you see what happened? I started with a general statement of Ohm's law. Then I told them, okay, I understand what changed now. And then I basically changed Ohm's law just to incorporate the specifics of the question. Okay, and that's your 3 marks. So first mark is just stating Ohm's law. Second mark is telling me that you know what happened to the resistance. And then the last one is just making it applicable. Okay, so now we are done with question 5. Now, to be honest, if I did this paper, I would only do it up to question 4. So I would do question 5.1, 5.2, 5.3, and 5.4 because I've been practicing and I like the sums and those are easy. 5.5 and 5.6 is a little bit overwhelming to me, so I would have left those out. It is only 4 marks, but because they are difficult, I'm giving my brain a little bit of a breather before I come back to the more difficult ones. Okay. Now, since we went from a parallel circuit to a series circuit, let's go back to question 4 and try that one now and see if it is as overwhelming as we think it is. So what's important to see with question 4 is that it's basically 2 questions. They're asking questions about circuit A and then they're asking questions about circuit B. So if you can differentiate that, then it's less overwhelming. So they asked define the term EMF, and that is on your definition list. So the voltage measured across the terminals of a battery when it is not providing current to a circuit is called the EMF of the battery. And you can just add the EMF stands for electromotive force. Now for 4.2, they asked the total resistance of circuit A. Now circuit A is just like a purely parallel circuit. And I am going to borrow the information list that I made for question 5 because I don't want to redo something that I've already done. Now I need to adjust this a little bit because I don't have a resistor in series. So what I'm going to do is I'm really just going to scratch these out, okay, because I only have the parallel ones. So they're asking for the total resistance of the current. So if I follow my breadcrumbs, my total resistance will be my parallel resistance, and this is the formula for my parallel resistance. Okay, so I'm just copying what I already know. So 1 over Rp equals 1 over, so it's 1.5 and 1.5. 1.5 plus 1.5. Then I'm typing it into my calculator. So 1 over Rp gives me a value of 1.33. But remember, I want to flip it around. I want to know what Rp is. So in my calculator, I'm going to say 1 divided by, and then I'm using my answer key. And then I get an answer of 0.75 ohm. Okay. And that is the answer. I suspect that you will get a mark here for the substitution or for the formula. I'm not sure yet. And then for the answer. Usually with these sums, if it's 3 marks, it's definitely formula, substitution, answer. If it's just 2, it's a toss-up between which one of these 2 will be the mark. But you're going to write everything so that you are certain that you will get all your marks. Okay, so we've done that one, we've done that one. Now for circuit B, let's just clean the page. Okay, and again, I copied the little formula sheet that I've been working with. And again, I need to adjust it so that it fits to my electric circuit. Now, because I don't have a parallel piece, I'm going to take all of this out. And instead of talking about Vp, I'm going to talk about V2. Okay, that being number 1 and that being number 2. So for 4.3, they ask write down the reading on A2. So A2 is this one over there. It means that they're asking for the total current. Now I don't have my information list yet, so let's make it there here at the bottom. So VIT, VIT, VIT. Now if you are very good with organizing information in your head, you might not need to make these information lists. Oh, and there's my answer. So they give me the total current is 1.5 there at A1. And because in a circuit, we know that the current is the same everywhere. That's what's happening there, right? Because I have this value, I have that value. And it also explains why this question is only 1 mark. For question 4.4, they ask calculate the reading on V1. Okay, now V1 is this voltmeter over there, and it is across the 2 ohm resistor. So if this is 1, and this is 1, and this is 1, then I can put a 2 ohm over there, which means I can put a 4 ohm over there. Now, because I used my highlighter, I can also write the 1.5 ampere there, and I can write it there. And as soon as I do that, I can see that I have enough information to determine V1. So this is really just V equals IR. I'm using the number 1 values from my information sheet. I is 1.5 and R is 2. So my answer here is 3. Okay, and I can always come and write it over there. Now, I have the total voltage of my blue circuit. It is 9. Okay, so if my total voltage is 9 and V1 is 3, then does it make sense that V2 should be 6 volts? Because 3 plus 6 equals 9. All right. I want to check whether I'm right or wrong. So what I'm going to do now is I'm going to do VIR with this information list and just make sure that I do get back to 6. V equals IR. And this is not for marks. This is for my own sanity and my own comfort that I know I am right. So 1.5 times 4 is indeed 6 volts. So if I take V1 that is 3 volts, and V2, that is 6 volts, and I use my knowledge about volts in the main circuit. If I add those two, I get 9, and 9 is my total volts. So I know I'm right. So they tell us if a third resistor is placed in parallel with the existing resistor in circuit A, which would be that one, would the total current in the circuit increase, decrease, or remain the same? Now, this question is exactly the same one as what we did here. So I'm going to copy and paste this. Let's call it a cookie cutter again, but I need to change it just a little bit so that it fits my question. Okay, so that's my reference. I'll come back to that now. So they tell us we start with a circuit that looks like this, and then it turns into this. And they're asking us a question about the total current. So we know we are going to use Ohm's law, and we know we are going to work with the total values. We also know that our total volt value is constant because I haven't changed my battery. Okay. So to figure out what's going to happen to I need to figure out what's going to happen to R. Now you can just immediately say that the resistance will decrease, or you can go and do a little sum. Let's pretend that each of these resistors have a resistance of 3 ohm. And we can do a little sum just to check what happens to the resistance. So 1 over Rp, we know that's the formula, becomes 1 over 3 plus 1 over 3. That is 2 over 3, but I want Rp. So I flip them around. So Rp will be 3 divided by 2, that's 1.5 ohm. And then for the next one, 1 over Rp equals 1 over 3 plus 1 over 3 plus 1 over 3. That's 3 over 3, which is 1. And then if I flip it around, it's still 3 over 3, which is 1. Okay, so I prove to myself now with a little sum that has nothing to do with the circuit that they gave me, that the total resistance will decrease when I add a resistor in parallel. And just like earlier, because my voltage remains constant and my resistance decreases, the current will increase because there is an inverse proportionality between I and R. So a better way of saying this will be by adding a resistor in parallel, the total resistance will decrease. Therefore, if the resistance decreases, the current will increase, provided that the voltage remains constant. Okay, so your 3 marks again. Now again, 4.5 is like a level 4 question, so if you are not in the mood or you don't feel relaxed enough to tackle level 4 questions, then leave it and come back to it later. Okay, now if you've been doing all these questions with me and you're still with me, then you will find that we are going to speed up a little bit, because all the questions that follow, they are pretty much just carbon copies of the 2 we've already done. Okay, so we are over the worst. Now you can just make sure about those little wrinkles, make sure that you understand what's going on. So question 6 says that 2 identical light bulbs. Now identical light bulbs tells us that the resistance of A will be the same as the resistance of B. And then we have that measuring device, and with our note earlier we said we know it's an ammeter, and it looks like this. So which physical quantity will device Z measure when the switch is closed? So they want to know what is being measured. So they're not asking for the name, it's not ammeter, they're asking for the word current. Okay, so 6.1 is current. Give a reason why the brightness of the bulbs will be the same when the switch is closed. Okay, so it's only 1 mark, and you can really just say that they will have the same current. So we know the number of fairies that comes out of the battery will be the same that goes through obstacle B and through obstacle A, so the current will be the same. And because brightness of a bulb is directly proportional to the current, and the current is the same, the brightness will be the same. So just in short, the current is the same. And then now they ask, a third identical bulb is now connected in series with bulbs A and B in the circuit. Will the brightness of the bulbs increase, decrease, or remain the same? Now, does it ring a little bell? We are back to this sum. So just to write some notes before we change the answer to fit the actual question. we know from our theory that the current will be the same everywhere. So it will be the same through A, it will be the same for B, and it will be the same for C if we put a C in there somewhere. Let's put it there. It doesn't matter where it is. Okay. And we also know that the brightness is proportional to the current. So again, we're going to write Ohm's law, and we're going to be working with the totals. Again, we know that the total voltage will remain the same because we didn't change the battery. We want to know what is going to happen to the current, and therefore we need to figure out what's going to happen to the total resistance. And we have a formula for total resistance. It's RT equals RA plus RB. That was the original circuit. And if we add another one, RA, RB, and RC, we can see that the total resistance will increase, right? So you can add little numbers, make it 2's. So 2 plus 2 is 4, and 2 plus 2 plus 2 equals 6. So you can see that the total resistance increases. And because there's an inverse proportionality, it means our current will decrease. And because the current will decrease, the brightness will also decrease. So this was only 1 mark, but we had to go through all this reasoning to get to the answer. So if this counted 4 marks, 1 mark will go for decrease, and then the other 3 marks will go for the explanation. And we obviously need to change this middle bit because now we're not working with parallel circuits. Okay, so according to Ohm's law, current is inversely proportional to resistance provided the voltage remains constant. By adding a resistance series, the total resistance increases. Therefore, if the resistance increases, then the current will decrease provided that the voltage remains constant. And I would maybe just add something that the brightness is dependent on the current. Okay. So again, for these two, I would do 6.1 and 6.2, I would do. And if I was feeling a little bit overwhelmed and not in the mood to do really difficult, like, well, not difficult, but level 4 type questions, I would leave 6.34 last in the paper. I don't want to spend too much time on 1 mark if I can rather spend it on something that's a little bit easier. Okay, question 7. Question 7 is, in the circuit below, potential difference V1 across the battery and potential difference V2 across the 4 ohm resistor are unknown, and then they ask us a couple of questions. So the first one is define the term potential difference. Now, when we did the theory in the previous video, I gave you a definition for voltage, and it said that voltage is the measure of the electric potential energy per unit charge in an electric circuit. Now, voltage and potential difference, they both have a symbol V, but the definition is slightly different. Where voltage is the potential energy per unit charge, potential difference we define as the difference of electrical potential between 2 points. Now, to help you make sense of the difference between the two, you can see the voltage as the energy that the fairies get while they're moving through the battery. So the fairy or the electron will come in through the positive terminal of the battery, and it will move through the battery, and then when it moves out of the battery on the other side, it has an added bag of energy, if you will. So that is the electric potential energy per unit charge. Now, if we look at potential energy, the easiest would be to imagine one of our obstacles or one of our resistors. And this is a little sum that we did all the time when we were busy with the fairies. So the electron will approach this resistor with, let's say, 10 joules. And it will exit the resistor with 8 joules. And when we subtract these two values, we get a value of 2 joules per coulomb. And that will be our potential difference. So the potential difference is exactly that. It's the difference of electrical potential between 2 points. Okay, now they ask, calculate the effective resistance of the 2 ohm and the 6 ohm resistance, V1 and V2. And for this one, I am going to redraw this and make my information list because I know now it makes me faster. Now, what I now did is I really went back to our previous question and I copy and pasted. So you can't copy and paste, but you can copy it with your hand. So it's exactly what you're going to do. And now we just need to add the information. Now, I want to implore you, please don't just watch. Please pick up your pen and do this with me. Okay, so we have the parallel voltage, so that's 4, and then we have 2, 6, and 4 ohm. So that is 4, that is 2, and that is 6, and we know the parallel voltage is also 4. And then I just want to do my highlighter before I forget. The I values are the same, and then my volt values are also the same, and then that means I can copy the 4 there and the 4 there. All right. And now again, you can either just fall in and do everything that you can and then make it nice and neat, or we can sort of help the questions show us the way. So the first thing they ask is the effective resistance of the 2 ohm and the 6 ohm. So that's just a fancy way of asking for the parallel resistance. They want that. So this is the formula that I'm going to use. 1 over Rp equals 1 over R2A plus 1 over R2B. And then from my information list, I can see my resistance is 2 and 6. So in my calculator, I put in 1 divided by 2 plus 1 divided by 6. That gives me an answer of 0.67. And then I can just flip it around, say 1 divided by answer, and then I get an answer of 1.5. And the unit there is ohm. So that value I can write over there. Okay, so that was 7.2. For 7.3, they asked the value of V1. Now, V1 for us is our total voltage. So let's see if we can get there. Now, for my total voltage, I need the total current and I need the total resistance, which I don't have at the moment. If I come up here, I can see there's also a VT. So if I use this formula, VT will be V1 plus VP. I do have VP, but I do not have V1. So that's sort of going to struggle a little bit. So what I'm going to do now is I'm just going to start with something, and I'm going to start here. Okay. So VP equals IP RP. Now what I love about this method is you do not really have to know where you're going. You just have to know where you are, if that makes any kind of sense. Okay, so now I get a value of IP equals 2.67 ampere. Okay, so it's 2.67 if I round, but in my calculator I'm keeping all those 6s. So IP, now this is IP, so it's 2.67, and my highlighter is reminding me that this is 2.67 and this is 2.67. Okay, so it means that I use that formula as well now. The next one that I'm going to do, you actually have a choice. You can either determine V1 and then use V1 to determine VT, or you can determine RT. Okay, so it just depends on what you see. So I saw V1 first, so let's do V1. So V1 equals I1R1. So it's 2.67 times 4. Now that 2.666 is in my calculator, so I'm just going to say times 4. So answer times 4. And then I get 10.66 volts, which is that value there, so 10.67. And now I'm using this formula to get my final mark. VT equals V1 plus VP. V1 I just determined is 1.67, and then VP is 4. So 10.666 is in my calculator, so I'm just going to say answer plus 4, and then I get a value of 14.67 volts, which is that value there. Now, in terms of marks, you are done. You have all your marks, but I really want to go check myself and make sure that I have all my marks. So I'm going to do two things. I'm going to do VIT for this one to determine R. So I'm going to use VIR to determine T. So that's 2.67 times, I don't know what R is, and VT is 14.67. So 14.67. I'm using round numbers now, because I'm just double checking myself, divided by 2.67, so then I get a value of 5.5 ohm. Okay, and if I use this formula, R1 is 4, and RP is 1.5, and 4 plus 1.5 is also 5.5 ohm. Okay, so I got to that 5.5 in two ways. I got it through Ohm's law, and I got it from our knowledge about how electric circuits work. And because I got 5.5, I know everything on my paper is right. Okay, and then 7.4, they ask for the voltmeter V2. Now V2 is the voltage over the 4 ohm resistor, which I think we already did. Yeah. So we determine it through our method of determining VT. So the answer is already there. You actually don't have to do anything else. What this does tell me, however, is that they actually wanted me to do this sum first to get to RT, and then use VIR to determine VT. Okay, so if you're a little bit confused now, it just means that there's a certain way that this specific memo was written, and I did it in a different way, but it's scientifically sound and everything is on my paper, so I will get all my marks. Yeah, and then we're done with question 7. Okay, question 8. So we have this little thing. This was not really a sum question. It's more knowledge. Do you understand what's going on here? So we have this little circuit, and I did redraw it over there. Let's just take this one out for now. And they say S1 and S2 are open. Which bulbs, if any, will light up? And we said none. Okay. None will light up, because if S1 and S2 are open, then the fairies can't move through there to get back to the battery. So no current is flowing, and because there's no current, there will be no lighting up. Then the next one tells us S1 is closed, like there, and then S2 is open. So if S2 is open, it means I lose this whole leg of mine, which also means it's basically just a series circuit. Compare the brightness of bulbs M, N, and P. Okay, now N, being in the leg that won't get any current, it will be dead. It will have no brightness. It will have no glow. Let's write no glow. It will have no glow because it won't have any current. And then because M and P will be in series, so if an electron comes out of the battery, all those electrons will go through P, and all the electrons will go through M. And because their resistances are the same, because they say they are identical, they will have the same current. And because they have the same current, they will have the same brightness. So N won't glow at all, and M and P will be the same. For 8.3, 4, and 5 is again theory. So parallel circuits can be regarded as current or potential dividers. So we were just speaking about the fairies and the current being split up by the parallel piece. So it means that parallel circuits are current dividers. Okay. Adding bulbs in parallel causes the resistance of the circuit to, can you remember what we did with this sum? It's exactly what happened here. So we went from 2 parallel globes to 3 parallel globes, and with this little sum, we prove to ourselves that the total resistance will decrease. So if we come back to this one, we can just write decrease because we already did the work. Okay, so adding bulbs in parallel causes the resistance of the circuit to decrease. And if you haven't done it yet, you will just do that little sum again. So 1 over Rp equals, let's work it with 3. Let's work with 4. So 1 over 4 and 1 over 4, and then you do a little sum. And then Rp equals 1 over 4 plus 1 over 4 plus 1 over 4. And then you do a little sum, and then you just compare them. So if you can't remember, do a little sum. Okay, and then the last one, 8.5, I think there's just really a mistake on the paper. So potential difference across the battery to increase, decrease, or remain the same. I don't know what that means, so I'm leaving it out. Okay, question 9, and then we're almost done. So again, this is a really easy one. They only have one resistor. The first thing is to define potential difference. We've done that, so I'm not going to do that again. Define electric current. So electric current was in our last video. So current is the rate of flow of charge, and it's contained in this formula. And then 9.3, the reading on ammeter A is that, and that's the energy, and that's the minutes. Determine the voltmeter reading. So let's just do it in pen. And what I'm going to do now, I'm just going to copy the formula so that I have them in front of me, because I have a feeling I'm going to use more than one formula because it's 6 marks. The other one is voltage. So voltage is energy per charge, and the other one was current, which is charge per time. All right, my information, let's say, is VI, W, T, and V. I is 0.6, W is 486 joules, and time is 180 seconds. Now I want V. I've got a V there, and I've got a V there. I also have time. There's a time. I have W, which is there, and I have I, which is there. Okay, now it seems like I can't do anything, but what would happen if I determine Q? If I had Q, then I can get to V, right? Okay, so let's start with this formula. I'm just copying. I equals Q divided by T. I'm substituting 0.6. Q, I don't know, and T is 180. And then to get Q alone, I multiply the 180 to the other side. So 0.6 times 180. And then my calculator tells me that the charge is 108. And I remember my unit, it's coulomb. So let's just add it there, 108. But I actually want V. So now I'm doing that formula. I'm copying because it's already there. W divided by Q. V, I don't know. W is 486. Q is 108. So in my calculator, 486 divided by 108 is 4.5 volts. Okay. And you have all your marks. You have your formula, your substitution, your answer, formula, substitution, and answer. So you have 6 out of 6. This one went really fast. Okay, last one. And compared to the others, I think this one is also really easy. So they say consider the circuit. The bulbs are identical, so I know again the R values are the same. And then they ask us calculate the voltage of all 3 cells if they transfer 90 joules of energy to 20 coulomb of charge. So it's basically the same that we just did here. So we want voltage, and we have W and we have Q. So this one is even shorter. So V equals W over Q. And then we have 90 divided by 20. That's just your substitution. And you will notice that I don't go back here to get the 20 and the 90. I just come back to my information list. So there's no chance that I can get confused, because I'm not worried about all these words, because I already managed them. I already used them. I don't want to go back. Okay, and then we get the same answer. This one is 4 marks, so I'm guessing it's formula, substitution, substitution, and answer. Okay. Now they ask us, what would the potential difference of each cell be? All right, so a little bit of theory, but I think you know that from grade 9. This total voltage that we have, which is 4.5, it is made up of the individual voltages of the cells. And I have 3 of them. So I'm going to say the total voltage comes from 3 of the little ones. Let's just call it I. So that if that is 4.5, then it means the voltage of a cell, maybe I should just make it a C, will be 4.5 divided by 3, right? So the voltage of each cell is 1.5. Now 10.3 is another little sum that I didn't even highlight. The charge of 30 coulomb of charge passes a point in the circuit in 40 seconds. Determine the strength of current passing through the main circuit. So again, we're back to this. Okay, other formula, but same idea. So the charge is 30, the time is 40, and I want the current. So that is time, that is charge, and I want I. Okay, so I copy I equals Q over T. It is 30 divided by 40, so it's 0.75 amperes. All right, so this one will also be formula, substitution, substitution, and answer. Okay, now they ask determine the current through each individual light bulb. So we have a parallel section, and we know parallel sections are current dividers. And if you are unsure why, it comes from this formula there. So the current in a parallel section will be split up. And because our resistors are all the same, we are going to say that the total current will be 3 times the current of every resistor, because they're exactly the same. So I know my current is 0.75. I just determined that. If I just divide 0.75 by 3, I get 0.25 amperes. Okay, and in terms of the ferries, we know that. So let's just work with 75 and 25. So if 75 ferries leave the battery, then 25 will go there, 25 will go there, and 25 will go there, because the obstacles are of equal difficulty. Okay, now for the last question, 10.5, it says, if one of the light bulbs burns out, how would the brightness of the other 2 bulbs be affected? Right, only shine brighter or shine dimmer? Now, it might feel, and it is actually this Ohm's law thing that we did previously. So according to Ohm's law, current is inversely proportionate to resistance, provided that the voltage remains constant. Okay, and we know that by removing a resistor in parallel, the total resistance will increase. And if the total resistance increases, then the current will decrease. And yet, I'm going to say that they get more current. Now, let's see if this makes sense. We know that the total voltage will remain constant. Okay, we know that the total resistance will increase, and that the total current will therefore decrease. Okay, but in this first scenario, we took our total current and we divided it by 3, because there were 3 legs. If I take one of them out, we will still have a total current, but now we will only divide it by 2. So although the total current will be less, as according to Ohm's law, it will only be divided by 2 and not by 3. So I am going to guess here, without any other information, that they will shine brighter. Okay, so there are still more ferries that will go through the 2 legs. It is only 1 mark, in which case I would probably have left it out and rather spent it on something else that I'm really good at. Okay, so we are done with the long form questions. Now we can go back to the short form questions. Now, because we did the long form questions first, you will see how fast we are going to do the short form questions. Now, for 5 marks, all in all, I have 6 minutes to complete this. And if you do this with me, even on your own, you will do it in less. Okay. Electric current is defined as the quantity of charge that passes a given point in a conductor each minute. Now, we've been using that formula like over and over now. I equals Q divided by T. So Q is in coulombs and T is in seconds. Okay, so this is what we know. Now let's just map it onto what they're giving us. So electric current is defined as, so that's your equal sign, charge, that's your Q, that passes a given point in a conductor each minute. But we know time is in seconds, so this one will be false. Okay. When 2 cells are connected such that the positive terminal of the first joins the positive terminal of the second, the batteries are said to be connected in series. Now, the first time I read this, I would have said, yes, of course it's true. But then when I did it with you in class, I did it the way I was supposed to, by analyzing each and every word. So they say we have a positive terminal of the first cell. So there's my first cell. This is the positive terminal, that's the negative terminal. It joins the positive terminal of the second. So if I add another cell, the way they want me to put it in, it needs to be a positive there and a negative there. And we know that's not the way we connect cells to make a battery. So this will be false. If this was negative, then it would have been true. Okay. Now we have a joule is equivalent, that's equal to a volt per coulomb. So we have a formula with energy, volt, and coulomb, right? It is volts is the energy per charge. So volts is the joules per coulomb, but now they want joule. Let's get the energy alone. To get W alone, I multiply the Q to the other side. Okay, so joules equals volts times coulomb. But that's not what they say. They say it's per, not the product of. So this is false. Okay, so if you had to write this in a symbol form, it would be W, that's your joule, equals volts is V per is divide, coulomb is your Q. Okay, so if you compare this that they're giving us to this that we know from the theory, we can see they're not the same. So it's false. The next one comes back to current. So 1 ampere is equivalent to 1 coulomb per second. And I actually wrote it down there when we started. So ampere equals coulomb per second. So this one is true as well. And then Ohm's law is V equals IR. We've been using it over and over again. Ohm's law states that the voltage is directly proportional to the current. That is true. We know V is directly proportional to I and indirectly proportional to resistance. So if your voltage is indirectly proportional to resistance, this is what needs to happen. Okay? But according to Ohm's law says V is directly proportional to R, not 1 over R. Okay, so do you see how we do the mapping? We see what they're asking us, and we write down what we know, and we compare. There's no real thinking going on there. It's more comparing. Okay, so I've been talking now in this little video, in this little section of the video for 4. Okay, so 4 minutes writing and talking for 5 marks. Okay. One word for a voltmeter. Now we're going to fly through this. A voltmeter is usually connected in parallel. Okay, so we know the voltmeter, especially with the battery, it's over the battery. It's not there. The ammeter is in series. A measure of how much charge is passing a certain point in a circuit in a given amount of time. So I'm just going to be a little bit lazy and come and fetch it here. I just want to make sure that I'm understanding it correctly. So the measure of how much charge is passing a certain point in the circuit in a given time. Okay, and that I, so this is current, because I asked the measure of. Then the apparatus used to measure the potential difference across a resistor, and we actually have the word there, it's voltmeter. So apparatus is the thingy, the thingy that you use to measure the voltage. That's the voltmeter. Thingy is not a scientific name. And then the amount of energy that the battery gives to every charge. So the only formula that we have W with energy is V equals W over Q. So the amount of energy that the battery gives to every charge. So W over Q equals V, that's your voltage. I wouldn't say it's potential difference, because potential difference is more the energy that's being used, not the energy being given to the charge. And then the law that states that current is directly proportional to voltage, provided that the total resistance remains constant. We only have one law, and that is Ohm's law. All right, now our multiple choice questions. These are also going to go very fast. So consider the circuit. How will the readers on ammeters A1, A2, and A3 compare? Now, when we did it the reading time, we made a little note over here. And I just wrote it in my own subscripts. I just want to map what I wrote onto what they asked me. So A1 will be your total current, and then we have A2 and A3. Okay, and then they're giving it in A's and not in I's, so let's just change that. So this is what I know. Let's see if I have it in my answer. A1 equals A2 plus A3. Hey, there it is. Okay, so I wasn't evaluating the answers, because that's really just going to confuse me. I first figure out the answer, and then I'm come and look for it. 3.2, they want to know about the voltmeters. So again, I made a little note. I just want to change it. So V1 and V2, I don't have to change it in this case. Which of these readings are correct? So here I just wrote that V1 will equal V2. Let's see if we have it. Here we have V1 equals V2. Now, if you want to make doubly sure that what you wrote there is actually correct, which by this time in the paper I think you should know that you are right, you can evaluate every single one. And if you are certain about your theory, you will disregard all the others. The unit in which rate of flow of charge is measured. So I just wrote out these, but from my formula sheet, I know I equals Q over T. And I is either current or ampere, depending on what they're asking. They're asking you for units, so that'll be amperes. Okay. Then we have W divided by Q from my information list or formula sheet. I know V equals W over Q. So that's my answer, and that's either voltage or potential difference. And there is potential difference. Right, and then ohm, I want to get R. So the only formula that I have with R is Ohm's law. V equals IR. And then I'm going to get R alone. So R equals V over I, because I divide the I away. Right. And if I use fancy words for this, it'll turn into volt or voltage per current. And if I use the units, it will be volt per ampere. So that's what I know resistance is. Let's see if I have the answer. So it's volt per ampere. Yeah, there it is. Okay. So I didn't even read the other ones, really. 3.6. The unit of measurement of electric current in ampere is what? We have two formulas for ampere, but the one I'm going to use is Q divided by T. Okay. So I is ampere, Q is coulomb, and time is in seconds. Okay, so ampere is coulomb per second. That's my answer. Let's see if I have it. Yes, I have it over there. Okay. So I'm not allowing the multiple answers to confuse me, because I first figure out what the answer actually is. And I know how to figure out the answer because I've been using these formulas over and over again. And I know that all the information that I need for circuits are contained in the formulas. Okay, almost done. Which one of the following statements about the resistance of a wire is correct? So I made little notes when we did the reading time. Now I'm just testing them. So the resistance decreases when the length of the wire increases. That's not correct, because I know length and resistance are directly proportional. So it's definitely not A. The resistance increases when the temperature decreases. That's this one. It's again not right, because from my notes I know there's a direct proportionality. So if the resistance increases, then temperature must increase as well. Okay, now there's an iron wire thing that I'm just going to skip for a second. And then I have resistance decreases when the radius of the wire increases. This seems right. So the resistance decrease when the radius of the wire, so the area of the wire, increases. Okay, so D is right. And then C is iron wire has less resistance than copper if both wires have the same dimension. So here you need to know the properties of iron and copper. And just maybe for future reference, is copper is a better conductor. So C is also false. Right. Okay. So again, I didn't really evaluate the words here. I just mapped it onto something that I already knew. And that I wrote down. Okay, so this one again, it's about the current being divided by a parallel section of the circuit. I wrote it in my own subscripts. I just need to make sure I use the same ones as in the question. So A1 is your total current, so that's a 1. And then the 2 in the parallel legs were called 2 and 3, and they used A's and not I's. So they're asking something about A2. So let's just look at A2 for a second here. Okay, so I can get A2 alone by moving A3. So it will become A1 minus A3. That's something that I definitely know. And then assuming that these two are the same, assuming that the two globes are the same, I can also say that A2 will be equal to A3. So if number of fairies here is 10, and the obstacles are of equal difficulty, then 5 will go through there, and 5 will go through there. Okay, so this is what I know. Let's test it. So they say A2, so they say A2 will equal A1. That is not true, it's not here. So A1 is my total current, and A2 is there in my leg. It doesn't make sense, unless that one didn't exist. Okay, so it's not A. Then A2 will be half of reading A1. Now this might be true. So let's use our 10 and our 5 again. So if that is 10, and that is 5, and that is 5. Okay, we know this is 5 and 5 because they are the same. So then B will be correct, right? So A2 will be half of A1. Then they also say A2 will be the reading on A3 minus the reading on A1. That's not true. It's opposite of what's going on there. And then A2 will be reading A1 minus the reading of A3. Okay, now this one is also correct. Okay, now I made an assumption that you're not really supposed to do in science. I assumed that these two were identical. Now, it helped me in a sense because it got me to yes, B is correct. But now I also have that D is correct. And now I need to decide which one I'm going to choose. Now, they didn't explicitly tell me that these two bulbs are the same. So it means I have to disregard B because D is more correct. So A2 is A1 minus A3, and that comes from there. And that came from myself. It wasn't the sum that led me there. This one was a little bit tricky. I would have left it till right at the end because you have to think really hard with this one. Okay, 3 more, then we are done. This one is a little sum. 10 coulomb of charge passes a point in a circuit in 2 minutes. What is the current? So I made my little information list, and I know my formulas tell me that it's I equals Q divided by T. Q is 10 and time is inches and seconds, so it's 120. And please do this on a paper somewhere. So I get 0.83 and I actually have 0.83 over there. Okay. Next one is resistors connected in series are called dividers of what? Now we've done this a couple of times, but let's just check again. We just did the fairies, so it should make sense. That's our battery. If we have 10 ampere going out there, 5 will go there and 5 will go there if they are the same, which means our current is being divided. So parallel circuits are current dividers, which means series circuits are voltage dividers or potential. And it comes from here. Okay, so you can see this is all our series, our main circuit. So our voltage gets divided in series, but the current remains the same. But in parallel, it's opposite. The current gets divided and the potential remains the same. And then the last one. It's all about voltmeters. The reading of voltmeters connected across resistors is inversely proportionate to the resistance. So that was Ohm's law, and we know that's not true. So according to Ohm's law, the voltage is directly proportional to the resistance. Okay, so that one is not right. When a switch in a circuit is closed, a voltmeter connected across a battery reads the EMF. That is correct. Voltmeters connected across equal resistors which are in parallel will give the same reading. So again, we know that's right. And if you are doubting yourself, just go back to the sums. Voltmeters are always connected in parallel. That's also correct. So we're looking for 2, 3, and 4. 2, 3, and 4. And that's my answer. Okay, well done guys for sticking with me. This was really long. But I hope more than just the circuits, I hope you saw the method of how I tackled the exam papers, the exam questions. And I'm going to do almost the same with all the other revision packs.